before we go further, are there any questions that is worth taking at this point before we move on?
Matthias, I want to make a question if it's possible.
Yeah, hi Pedro.
Hi. You were saying that the PVT is critical, obviously, for all this, for the assessment of in a EOR project. When it's better to have that PVT, to have it in when the well it starts to produce, or at the moment when you want to implement the EOR project?
Yeah, so that's a very, very good question, and we touched a little bit on it before the break. So I guess how I interpret this question is the reservoir fluid that you're supposed to loop into the PVT cell and that you're going to do these different experiments on, should that be an in situ representative sample, or should that be a sample that can be sampled after 3 years of depletion type of thing? And most likely the components in the reservoir fluids that's close to your fractures will probably be, at least at time of implementation, closer in terms of composition to what you're producing at the time of implementation or later in life. But that said, these key mechanisms and these key properties that you would like to measure in the PVT laboratory, like first contact miscibility pressures, or in a conventional flood, which would be multi-contact, they're not very dependent on necessarily the solution GOR of your reservoir fluid, or of the reservoir oil phase, essentially. So the oil saturation part of your system. So for these purposes, I won't say it's super critical, but the most important thing is to find, okay, in that pore volume that is accessible for gas to mix with oil, what is the fluid composition of that? And then you use that composition and you make an estimate of that. There's different methods of how you would get at least a very good estimation of that, but just sampling surface samples, recombining at the producing GOR would be a very good starting point, at least for that.
Okay, thank you.
Good. But for like, if you want to have and that's just for the experiments, right? And the experiments you tune to an equation of state model anyways. So what's important is that you have an equation of state model that replicates whatever fluid that you actually have in the PVT cell and where you do the experiments, but that when you actually do the reservoir or well simulation model, or create that model, then what's important is that you initialize with an in situ representative fluid sample. And to do that, there's a couple of papers. We have one paper for unconventionals, and the method is called, let's see here, it's a so-called ECM method, which stands for equilibrium contact mixing, and the go-to paper from 1994 is by Fevang and Whitson. This is for conventional reservoirs, while we wrote or essentially described the same method for conventional reservoirs last year, which is a paper that I wrote together with my colleagues, which discusses ECM for unconventional reservoirs. Just to so shale reservoirs essentially. And the problem statement there is okay, let's say you have a well again that has a producing GOR, which I call RP, and it's increasing at some point late in time, and you want to implement gas EOR right here. You have no PVT data early, and the only sample you have available for sampling is this. How do you actually use the sample accurately and thermodynamically correct to to estimate this initial fluids composition that we call an I think in situ representative fluid sample. There's some elegant, very accurate methods to do that we've described in that paper. They're very pragmatic and simple, and we also compare that to just simple recombination of separated gas and separated oil that you sample here, but that you recombine it at the initial producing GOR. And in some cases that will give similar results, but for near critical fluids, volatile oils and whatnot, this can be quite large in comparison to ECM. So but that's a different issue. And I guess my main point there is that the experiments that you do in the laboratory, why are they important? They're mainly important to have the relevant data to tune your equation of state thermodynamic model to. And when you create actually a gas huff and puff assessment, you need to create a reservoir simulation model anyway. And in that model, you need to input the in situ representative fluid sample, history match your production rates, and implement gas huff and puff at the time of whenever that time of implementation is.
Great, thank you.
Yeah, thanks. Yeah, so I think we should be good. Anything else? Or we can go forward, I guess. So what I'm gonna, probably me and Stian, I'm gonna mention too many times now. And what we'll try to convince you of is that for gas huff and puff EOR recovery to actually or that uplift to actually be a true physical uplift, we need to have some type of complexity around or a complex fracture network, small pieces of rock that allows for gas to mix in contact with the oil. Because of the low permeability nature of these shale reservoirs, all the gas EOR gas uplift must occur near the wellbore. And here, the wellbore can almost be considered as like a frac is almost like a wellbore. So it has to be close to the fractures because of the low permeability nature of these systems. And what is near wellbore? That's mentioned here. So that can be hydraulic fractures. They can be propped with high conductivity conduits. Very near to the fractures, you have matrix, which is the investigation of the gas that by diffusion, for instance, is not very large. It depends on, of course, permeability and porosity and diffusion coefficients and pressures and whatnot. But that's important. If there's any natural fractures, the Ratterman paper is really. And if you talk to the people that wrote that paper, the original paper with Helen Farrell and Ratterman that did the characterization there was essentially very few, at least in the Eagle Ford, natural fractures to be observed. So I think they counted 2 fractures before completion, and then just hundreds of fractures after. And after talking to these folks, at least in that paper. They actually, after a couple of years, changed their mind and actually starting to think that those 2 fractures that they had characterized as natural actually was hydraulic fractures from a very far away completion job. And then this thing that we call the shattered volume, other people maybe call it other things, but for all practical purposes, it is a stimulated area that has smaller pieces of rock. We've created complexity, shear failures and whatnot, where gas is allowed to contact essentially hydrocarbons or reservoir fluids on a scale that matters for huff and puff. So then we have to remember that that's like days to maybe 30 days, days to month type of scale. This is a kind of a cartoon of a shattered rock volume, I guess. So you have maybe a main type of fracture coming out of some cluster right here, or depending on what completion if it's a sliding sleeve type of completion, it will be more like a stage. And then if you get these people that know fracture characterization and whatnot much better than me, you would probably get a drawing of some type of complexity. Maybe it's some branches there, but there's at least a lot of fractures, many more fractures than clusters that is at least reported in these field observations. And that additional surface area, those small pieces of rock, that's we're going to look at that. That's really what creates the target and possibilities for uplift. Then we talk about a shattered volume, and we talk about that smaller pieces of rubble will essentially be more efficient, or you'll have a quicker recovery response from smaller pieces of rock. And what actually matters is the shortest diffusion path, such that the main flow in direction of the smallest dimension. And Stian has done some very excellent work on that. That's also been verified by experimental results with ERC among others, where for purposes the minimum dimension here, and here is the same, even though the total geometry is very different. And what's the main importance is, okay, what's the shortest distance that I guess these components can travel in terms of, for instance, diffusion. So the actual geometry is not critical, and Stian will go through that later. What happens near wellbore? Where does these are questions that we have to answer. Where does the gas actually flow preferentially? Where does the gas actually stay? Where does it escape? And where, most importantly, does it recover oil, and potentially why? So what we need to model in terms of from a reservoir simulation perspective and from our own understanding perspective is obviously, since we have fractures, we need to be able to model that, but also where the additional hydrocarbons will be hopefully recovered is in the fractures, in the matrix. So we need to also capture this fracture to matrix type of component, and here there are, at least on a generic basis, a lot of different possibilities of what can create uplift. And one of them could be displacement, but as we have discussed, and what you'll be also convinced after this course, is that this is of less importance for Huff and Puff. One is just the nature of that process, but it's also based on simulation results, and we'll look at that. Is very, very important. So that's the PVT phase behavior part. So swelling and vaporization, that's mechanisms after mixing has been I guess achieved. Miscibility is also related to it's also a PVT part that we've talked about, which is very relevant. Gravity, at least in the matrix, in this low permeability systems, is not that relevant as it would, for instance, be in a conventional type of flood with gravity segregation and whatnot. While the diffusion, as we'll see, will be relevant because that's our pathway for mixing. So diffusion deals with the mixing, and once mixed, these guys right here will help us, which is PVT related, to recover hydrocarbons, additional hydrocarbons. What's interesting, though, is actually that all the different things that we need to study and all the different things that we need to understand in terms of physics, in terms of modeling, in terms of evaluation in 2017. So this slide was actually made in 2017 for a SPE forum, but there is the same to today. Is exactly the same things that we had to understand back in the late 80s, when we were trying to understand, or when ConocoPhillips and Petrofina did nitrogen gas injection studies for the Ekofisk field in the North Sea. And for those of you those who know the Ekofisk field in the North Sea, that's the first oil field found on the Norwegian continental shelf, and I think it was found in 1969, and is one of the largest fields operated by ConocoPhillips, extremely successful. I guess now they're doing water flooding there, but they evaluated nitrogen gas injection, and all the papers from that is published. So a lot of the physics that we need to understand at this point is also relevant for what we need to understand now for unconventionals. So in that sense, a lot of these concepts, a lot of this physics is not new, but it's maybe as a good term many times that I've heard many times at forums is new things is just good old forgotten stuff, which is I think the case here. And as we'll see further when Stian will go through essentially the different observations from reservoir simulations, tying that into gas EOR rock experiments done mainly by ERC. I think we had some ERC folks with us here. They've done some excellent work up there, keeping the experiments simple, and we'll look at that as well. But for the purposes of gas huff and puff, the near wellbore region needs to be characterized to correctly evaluate the efficiency of huff and puff. The rubble geometry, and this is what we're going to see in the next session, is not very important in terms of how quickly you can recover hydrocarbons with the gas huff and puff process from a particular piece of rock. For instance, this guy right here. There are several of these non-wellbore region issues in unconventionals that already have been studied earlier, and we just need to apply that in a consistent and correct way also when we look at unconventionals. So, now we actually haven't shown a lot of the results, and we haven't discussed a lot of the reasons why it is like that, but we've talked about the importance of complexity when it comes to recovery. So what I would like everybody to do now, just on a piece of paper, and think a little bit for themselves with this exercise, is to sketch the recovery profile for each layer in this. I guess this is kind of like a layer cake where the complexity is increasing downward. So I guess this is a more fractured bench than this guy, which is more fractured than this guy, and then there's essentially no fractures or complexity created here. And then we have a huff period, a soaking period, and a production period right here. And I guess what we would like to see is a comparison of the uplift response compared to just primary depletion right here for the different cases. So, and rank 1, 2, 3, and 4. And I'll give you guys one minute, and then we'll or 2 minutes, and then we'll do this thing together. Anything to add here, Stian?
No, not really. Just yeah. So just to emphasize the point here, the point is to draw the production from each layer individually.
Yeah.
Where you think it is.
Yeah. So 4 different lines. That's what we need on this plot. That's to activate a little bit of thought process, and yeah, it's more fun when we do it live because then we have to show our drawings, and my drawings is always the worst. But most important thing is to be correct. So let's think about that for 1.5 more minutes, and then we'll get together. Okay. So does someone, at least with words, try to describe how they think it looks like? Someone that dares? No wrong answers, or there's maybe wrong answers, but nobody's gonna shoot anyone. So just checking. Yeah, nobody would like to go, so I'll try to sketch it myself, and then Stian will say if I'm right or wrong. So the only thing we know is that yeah, this is the recovery prior to depletion. So during the, at least what we know is that during the Huff cycle, we're not producing any incremental oil, which is what is plotted here on the y-axis. So this is cum oil production or recovery factor. Two sides of the same story. And we're not producing anything additional. That is like that for all the cases. During Huff, during soaking, we're not producing anything either. But then we're putting this stuff on production, and in the cases where we have no complexity, no fractures, just a planar matrix block that we inject gas into, and we do that in a huff and puff style, we'll essentially get zero incremental recovery from huff and puff. So this first line right here is line number 1. And then the more and smaller pieces and the more complexity we've created, the more uplift response we'll get. You've seen that answer now, and then we'll look at the experiments and the reasons why this is the case as we move a little bit forward. What I can say, however, just on a generic basis, for those of you who have seen a diffusion type of equation before, like a basic one, so like for instance Fick's law, for instance, we know that Fick's law is essentially saying that we have this is the diffusion coefficients, and this is the concentration of component I divided by the length. And if you study these basic diffusion coefficients like this, you'll see 3 things. That there's 3 things that can help with diffusion and mixing. The first thing is obviously the diffusion coefficients themselves. Jan will talk about that. Diffusion coefficients, they are a metric to quantify the I guess how efficient your diffusion process is at different conditions, and they're actually a function of pressure, temperature, and composition. But for simulation purposes, we assume that they're constants. Large concentration differences. The second point, differences, and the third one is smaller distances, the dx here. And what we're actually trying to quantify right here is the so-called molar velocity of a component. Okay, that's the people within the train. So these 3, so diffusion coefficients, large concentration differences. So if the injection fluid and reservoir gas or reservoir fluid is very, very different, that's in terms of concentration, that's good. And also small distances, or distances, right here. What we're essentially saying here is that for all these different layers, the the reservoir fluid is the same, the temperature and pressure is the same, but that's the assumption. So the diffusion coefficients will be the same. Because we're injecting the same gas, and the reservoir fluid that's there is the same. The concentration differences are the same. So the last thing that's the difference in terms of these different layers is the distances, and the distances is just, okay, is this rubble size 1 inch times 1 inch, or is it 1 feet by 1 feet, or is it 10 feet by 10 feet, type of thing. That's what we're trying to convey here and with this experiment. Yeah, and here we actually have the answer as well, which probably was provided in the slide deck, if I'm not mistaken, maybe not. So learning here is that if you take a gas huff and puff process, you make a planar fracture model. If you only have a fracture in a kind of symmetry of element reservoir simulation model, for those of you who are in this space, and you inject gas, and then you produce gas in a gas and huff and puff manner, you will get no incremental recovery from that process. So this is important if you're not including diffusion or any type of dispersion, these two things that we talked about. If you get any recovery, even if you have not put these things on, it's always due to what we call artificial. It's not artificial numerical dispersion. Okay, so this is numerical dispersion, which is just an artifact of the numerics of solving these equations with a simulator. And the numerical dispersion is increasing as your grid blocks get larger. So this essentially means that you get artificial mixing due to the fact that you're using way too large grid blocks in your reservoir simulation model. And a lot of the uplift that you see is not due to physics, but it's simply just due to numerical dispersion, which is just an artifact of numerics. Maybe you would like to add something here, Stian, because this is a key point that you'll touch base on many times.
Yeah, so here the diffusion about dispersion comes in again, right? Because dispersion, again, is a word used for many things. The mathematics behind this is something I can discuss with you offline if you want. I'm not going to go into depth of it here, but it's essentially, as Matthias says, it's the larger the grid block size, the more you have to, the picture you have to have in your head is that a grid block in a reservoir simulator is a PVT cell. And the bigger that PVT cell is, the more you can fill it with your reservoir oil and also injection gas. And we'll get back to this, but I just want to sort of try to draw a picture here. It's just that the bigger the reservoir blocks is, the more mixing you're forcing the model to have, because what should be a very sharp displacement front becomes smeared out by the coarse grading. That's essentially the key. So, but we'll get back to that and show pictures of it and the consequences of it, like numerical simulations. But it's just, that's what Matthias is trying to get at here.
Since we discussed, hopefully this is not confusing, but kind of the irony of this is that in a conventional displacement process, having large grid cells would actually be a conservative thing to do. So it will essentially give results that are worse than the reality. While for gas huff and puff, it's the opposite, that large grid cells will always give too optimistic salts. That's why it's extremely important to do what we call a grid sensitivity study before you do the final simulation run, such that you know that you have a converged, or that your simulator and I guess the equation that they solve actually has reached a converged solution. And what means by that is that when we increase the gridding size, then the total recovery or the total production doesn't change, or the uplift response doesn't change. And that's just one way to check it, and we'll go back to that. Yeah, and we've talked about this earlier. Yeah, and this is a little bit of the same thing. What we would like to do now is essentially show a drawing, and this is from actually 2017. It was one of these Gas EOR forums in tight unconventionals that Curtis was invited to be a speaker. Curtis Whitson, that is the founder of Whitson, at this SB forum, and he showed two different drawings. This recovery factor right here for different pieces of rock with the same length. So length here is constant. That's what it says. All of the lengths are 1 meter, and we have diffusion applied, but the permeability is different. And the higher the permeability, the higher the recovery, or the more efficient that recovery process is. Then a few, maybe just after that, or maybe a year after, ERC has presented these type of experiments for a wide range of different rocks, where you essentially say that this is the low permeability case. Everything else is the same rock, but just tested for different pressures. And we see, just for the sake of consistency, after 24 hours, we're about 50% for the low perm case, and we're about 100% for the high perm case. So this relationship is true in general. More importantly, or maybe more relevant for, permeability is kind of given as is, but the rubble sizes and the complexity and the surface area that create is a function of completion, which is something we can at least engineer. So the assumption here is that the permeability is the same, so it's the same, it's constant in all the different lines, but the difference is the minimum dimension of these different pieces of rock. We have one that's 10 centimeters, we have one that's 100 centimeters, and then we have one that is 1,000 centimeters. Yeah, and this can be feet for that matter. And we see that the recovery efficiency is getting higher as the rocks get smaller in terms of minimum dimension. So the diffusion path is smaller, and again, this was just a hand drawing made in 2017. Then ERC provided results again last year for, this was CO2, but it doesn't matter really what gas you use, where this is the smallest dimension. This was the minimum dimension in this case was around 1 millimeter. In this case, it was around 3 millimeters, and in this case, it was 11 millimeters, the diffusion path. And as we see, the recovery efficiency is definitely correlated with the length of these, or the dimension of this minimum, or the minimum dimensions of these different geometries, even though very different geometries. And we're actually conducting experiments with the ERC as we speak, actually, for hydrocarbon gases that's similar to this, but that is not only at constant pressure, because that's the important thing about these experiments that we show here. All of them are conducted when P is equal to 5,000 psi, which means that the pressure is constant. And when pressure is constant, convection is out of the picture, right? Because the train is standing still. So there's no delta P here. So there is no convection or Darcy flow that can help the components to move around. So the only thing you actually have that can work in your favor is diffusion. And that's what these experiments from ERC that we've also attached, or I think that we'll attach in the post course files, shows very clearly. And they've presented tons and tons of papers on this, and all the labs have also shown that as well. Obviously, this is a lot of Bakken rocks, but these things are true in general. So anything to add here, Stian?
No, I think that's that was good enough for now. We'll get back to these core experiments in detail a little bit later.
Yeah. Yeah. And this is just some cartoons that we have for in the slide deck. And in reality, what many times happen in the field is that when you have your bottom hole pressure drops like a rock, and then you start to produce at something that's close to constant, and then you're going to implement gas EOR. And you want to cycle your bottom hole pressures up and down like this because you inject that constant rate, and obviously your bottom hole pressure, or hopefully your goal is that the bottom hole pressure goes up. But many times in the field, or at least a lot of the production that you produce in the field will probably make such that you end up with producing fluids while the bottom hole pressure is between the saturation pressure of your reservoir fluid and less than the minimum miscibility by first contact. And if that's the case, the first few cycles, you'll see that the recovery efficiency is very high. It will be a swelling driven process. But as what we saw in the gas HnP experiment earlier, we essentially switched to a vaporization driven process after a while. So what happens here is that we have a very high recovery efficiency in the beginning. That's what I call EV, and then now EOR efficiency right here, and then that drops off after we reach this vaporization period, and this is also a gradual increase. And that's EOG, for instance, they do projects in one place, and then after a few cycles they move the compressor to another location. Yeah, and this is just a summary for reference in the slide deck that I think is good. But the key takeaways is that miscible huff and puff in an unshattered rock will yield essentially no incremental oil recovery. We'll show the simulation evidence for that a little bit later, won't we, Stian?
Yeah.
Anything else? Still?
No. I don't know. Are you referring to something specific, or?
No, I was just wondering about. Yeah, I think we'll show the simulation results of this later, and this has also been verified by a wide range of other authors as well. Canfor and Clarkson, I think, was the first ones to document that in 2017. I think. Yeah. So the main recovery mechanisms that we talked about is Darcy flow. We need to increase the pressures. Where essentially molecular diffusion is what creates and causes mixing, and once mixing is achieved, we have oil swelling and vaporization that can help in our favor, depending on whether or not we're single phase or two phase. Meaning, if we have a reservoir fluid at single phase only, or if we have both the liquid and gas in the reservoir at those conditions. Laboratory experiments that suggest that rubble size, so the size of these different pieces of rock, and matrix permeability are largely affecting the incremental recovery, which is consistent with the main recovery mechanisms here that we've identified. Good. So before we go in and revisit